Training an artificial neural network essentially means executing millions of matrix multiplications. To train even a basic model, you must run these parallel operations simultaneously on a truly massive scale. Standard CPUs process sequentially, meaning a single training run takes weeks. GPUs contain thousands of small cores designed to execute parallel operations, reducing that exact same workload to hours. The software bridge making this possible is the CUDA ecosystem, which optimizes these hardware calculations specifically for the mathematical demands of neural networks. Because deep learning relies entirely on this parallel math, the physical architecture of your hardware dictates the limit of what you can build. The market presents a sprawling range of hardware options. You can spend $200 on an entry-level consumer card or tens of thousands of dollars for industrial chips. Making the correct choice comes down to managing two specific physical bottlenecks: your VRAM capacity and the computational speed of your tensor cores. If you underinvest, insufficient VRAM will cause memory bottlenecks, crashing your deep learning projects before they even start. If you overinvest, buying a high-end card for a simple neural network leaves massive amounts of expensive compute power completely dormant. The goal is not simply buying the fastest card available. It is finding strict architectural alignment between your hardware's memory and your specific AI project's scale. The entry-level tier consists of cards like the GTX 1650, 1660, and RTX 3050. Looking at this pyramid matrix, the bottom layer represents strict physical limits, only 4 to 8 gigabytes of VRAM and weak tensor cores. We map these specs to capable projects, reliably training linear regression models, small multi-layer perceptrons, and simple convolutional neural networks. These cards are highly accessible and budget-friendly, but they are not built to sustain deep, modern neural networks. They work well for executing basic educational code, but should not be used for novel research. The mid-range tier introduces models like the RTX 3060, 3070, and 3080. The second layer of our matrix introduces an architectural upgrade: 8 to 12 gigabytes of VRAM combined with high-precision FP16 calculations. FP16, or mixed precision computing, manages VRAM usage by compressing the math, allowing you to train complex models efficiently. These specifications provide the necessary memory and precision for training deep CNNs, ResNets, medium transformers, as well as LSTMs and GRUs. You pay a higher upfront cost than the entry models, but you acquire the precision required for practical student projects and independent research. This tier provides the most efficient balance between financial investment and practical deep learning capability. The high-end tier introduces massive RTX 3090 and 4090 GPUs. This third layer represents the limit of local consumer hardware, massive memory, and advanced tensor cores. These let you locally train advanced vision transformers, generative adversarial networks, and GPT-2 scale architectures. Operating here introduces severe trade-offs. You avoid recurring cloud computing fees, but you must manage massive upfront capital costs, immense power draw, and heavy thermal output inside your machine. High-end cards are a logical investment only if your project requires strict large model privacy or the complete avoidance of cloud dependency. Industrial data center GPUs like the Tesla V100, A100, and H100 occupy the top of the compute hierarchy. The capstone of our matrix is physically detached from the lower tiers, representing the cutting-edge acceleration required to train foundation models. These powerhouses are specifically engineered to link together in enterprise clusters. They do not belong in a PC chassis under a desk. They offer unparalleled scale, but the sheer cost makes local ownership effectively impossible for individuals. If your objective is training foundation models, consumer hardware is totally irrelevant. You must rely on institutional infrastructure or expensive cloud rentals. To apply this, we can shift away from reading hardware specs and look at this decision tree, starting directly with your primary end goal. If your goal is learning the basics, your mandate is to not overbuy. You can access the CUDA ecosystem cheaply by sticking strictly to the entry-level tier. If your goal is deep learning research, high VRAM capacity and mixed precision compute become non-negotiable priorities. Your focus scales into the mid and high-end tier, depending on if you are processing massive data structures like GANs. If your goal is building foundation models, you abandon local hardware instantly. Your only viable path routes to the cloud and data center branch. Navigating this matrix successfully prevents catastrophic project failures from memory bottlenecks, while keeping you from wasting thousands of dollars on dormant compute power. The hierarchy of GPUs is a ladder of strict architectural necessity. Define the mathematical demands of your neural network on paper before you ever look at a hardware price tag. Match the exact mathematical scale of your model to the physical memory of your GPU.